Okay, thank you very much. Thank you for listening to my talk remotely. I hope that as things go along, if you have questions, I suppose reserve them till the end, and we can talk about them then. I'd like to talk to you today about what we call E4S, the Extreme Scale Scientific Software Stack. It's a product being developed within the ECP, but for open collaboration, and which is part of why I wanted to speak with you today to explain opportunities we see for potential collaboration with this community. I want to provide a little bit of context for E4S. We are within the exascale computing project. The software technology area is one of three focus areas. There's application development, which I believe Jeff Vedder mentioned in his first talk today, hardware and integration, and then software technology is the area that I lead. And the E4S efforts are within software technology. Within the software technology, we have 6 technical areas. One of them is the programming models and runtime, which is things like the MPIs that you heard spoken about today's OpenMPI, MPI-CH, OpenMP efforts, and we don't own the product in this space, but we make contributions to them. With a particular focus on the things that are the US exascale platform needs, in particular the plus of MPI plus X, where the X is a very large collection of accelerated devices. So that's something we care a lot about right now. This area also has things like Cocos and Raja, which are portability layers. Some of the more specialized efforts in PGAS, for example, UCC++ and GasNet. And then efforts in tasking, Legion, and Parsec. And then also some libraries for deep memory hierarchy management and power management. In particular, in the power management area, there have been some nice new developments. The second area is development tools, which Jeffrey Vedder leads. And so this is, we reorganized the project within our portfolio last fall and put all of the LLVM efforts within Jeff's area because we saw that as an important portfolio to manage very deliberately. And so we put that in Jeff's area. We also include in here our efforts for the Flang of F18, the new version of Flang, and also some performance analysis tools, things like PAPI, Tau, HPC Toolkit, and so on. In the math libraries are things like PETC, Trivinos. We have a couple of new FFT projects, sparse solvers like SuperLU and the follow-ons to those, and a variety of other similar capabilities, dense linear algebra in particular. And then in the data and viz area, we have the I/O libraries like HDF5 and audio. We have the Alpine project, which you can think of like things like ParaView and related VTK. VTK-M is the new parallel node version of VTK. And then these are the 4 main technical areas where we have a lot of deep work going on in product development, new algorithms, new implementations, and delivery of those. The 5th area is software ecosystems, which is our effort to then organize and put out the product that we are developing. So we say we deliver capabilities and we put them out in our open source repositories. For the purposes of ECP, the hardware and integration focus area, one of the 3 I mentioned, works closely with us and with the facilities, things places like Argonne, Leadership Computing, Oak Ridge, NERSC, and Lawrence Livermore, to then deploy these capabilities into the leadership centers. But of course, these are open source products, so many other people use them within the labs and all the way across the world. So we're really focused in the software ecosystem area in providing new technology, new workflows, ways of getting the work out the door. This effort also contains enhancements to SPAC, the source package manager, and also in containers work that we have going on. The sixth area is the NNSA. This is the National Nuclear Security Agency. It contains the open source products that are primarily developed at the NNSA lab that have an outward focus, where the intention is to collaborate with the broader community. And we put all of those into a single technical area to help manage the interface between the science labs, open science labs like Oak Ridge and Argonne, for example, and then the NNSA labs like Lawrence Livermore, Sandia, and Los Alamos. So that's the six technical areas. This is just the leadership team here. I won't go into detail myself, but I think you probably know a few of these names. At least, of course, you know Jeffrey, Rajiv, Sherry Lee is our new math libraries lead. Lois McKinnis has taken over as the deputy director. Jonathan Carter has become the new associate lab director, taking over Kathy Yeller's position. So Lois has stepped into this new role, and so on. So you can see some of these people. What do we work on? We work on the products that you may know, and then the MPI, the OpenMPs, as I mentioned, all of these capabilities are things that you know, and we're extending them for the purposes of accelerated architectures. One of the legacies we anticipate from the exascale computing project is a portable software stack that not only runs on a hosted NVIDIA accelerator, but also runs on a hosted accelerator from Intel and from AMD. One of my great interests in speaking to this audience is we don't have a target right now for accelerated ARM processors, the SVE extensions to ARM. And to us, that's very interesting, and we would love to be able to coordinate activities and learn from the Fugaku system and similar targeted platforms as we prepare the stack, because we care about portability not only to the targeted exascale platforms, but to all platforms that are coming in the future that we view as a really important HPC system. And the ARM Fujitsu processor is very interesting to us and important. Just a slide that shows the 33 projects. These are the lowest level projects that are part of the software technology area. And each has a PI, each has a project coordinator, and they're roughly evenly spread out across the technical areas, except for the last two, which are special in some ways, but I won't get into those details. Again, here you'll see Jeff's name. He not only leads the development tools, he also leads one of the important projects in the Proteus Tune effort. So a little bit of an overview of E4S. To start off with, I want to mention that part of what CCP is doing is funding and coordinating activities across individual project teams. These are teams like the PETSI project, the Super LU project, the MPICH project, the audio, the HDF5. These are projects that have existed before ECP and will exist after ECP. And so in some ways, we're kind of the funding source of the day for a lot of these projects. And so these teams, in many ways exist in the same way they always have. What we're adding, because of the scope of ECP, the size of the project and the ability to work across all of the major labs and a bunch of the universities, is we can add some new layers. And this is our opportunity to actually take these small teams and work with them as a portfolio of related products. And that's the exciting part of what we're trying to bring in with our software development kits and the E4S platform as a whole. The first component of this architecture that goes beyond just the individual product development are the SDKs, the software development kits. These are groups of similar products that they provide similar capabilities. They may be used in combination or be used as swap-in compatibility layers for each other. And we're creating the ability for these teams to work together, to coordinate activities and delivery, to develop community policies that provide them with the opportunity to have a higher level of service, quality commitment to their user base, and to adopt best practices as the community has defined them. I'll talk a bit more about those in a minute. And then the highest level layer is E4S itself, which builds all the SDKs, and it builds a complete HPC, high-performance Linux type environment that contains not just the ECP products, but everything that's needed by them as well. And we use SPAC to do the installation, and we provide containerized versions. We are building up continuous integration testing capabilities using the SDKs and E4S, and trying to provide a complete, what some people would call a DevOps experience for our developers, and getting things stably with high quality to the users as we do our work. This is what E4S contains. It's a curated release of the SD products using SPAC. We have binary build caches for bare metal installs for each of these targets. You'll notice the ARM64 targets. We have container images on Docker Hub and E4S, and a lot of other containers. We also have support now for DPU, both the AMD and the NVIDIA GPU targets. We have GitHub recipes, integration with GitLab, a validation test suite, and a bunch of other container types. And then an Amazon AWS image as well. And you can get access to all of this by going to e4s.io, our primary website. We've done a few releases now. We most recently, just this month, did release 1.1 just before our ECP annual meeting. And we have now 50 full products of the 70 that we contribute to. 50 are fully available in E4S, and we have 10 that are partially available. This is just a list of the things that are in it. Again, I won't go through these details for your reference. The slides you'll have later. Okay, I want to talk just a little bit about SPAC. I'm guessing most of this audience knows about SPAC. SPAC, again, existed before ECP started. We adopted it as our from source build tool. SPAC grows in its capabilities, including build caches now, so that if it sees a particular build signature in the build tree and it has a binary cache of that, it doesn't have to continue compilation. It can simply pull things off that stack. It's been very effective at the leadership computing facilities at some of our larger computers. Build systems, going from, say, for example, for Aries, the system went from 2 weeks to 3 hours. For Summit, the latest big system at Oak Ridge, we went from 2 weeks to 12 hours overnight build. So we've seen some real value using SPAC. SPAC is not a developer tool. It's truly an installation tool. And so, we don't propose it as a replacement for, say, something like CMake or AutoComp, AutoMake type of thing. But it's really good at being this meta build tool, and it's continuing to gain new capabilities month by month. We use it to deploy on our leadership systems. I don't know the details of what's being done with Fugaku, but I know that there's an effort that Todd Gamblin has with Riken to use SPAC. You probably know more than I do about that, but it's here, and I wanted to mention that. It's used worldwide. These statistics grow month by month. And then it's used on both bare metal landing containers, so that as a part of ECP and at the leadership facilities and more broadly in the HPC community, we see that container environments are absolutely critical to our efforts going forward. And we want to be prepared for that by making sure that our software can be available optimally in those kinds of environments. As I mentioned, we use it in our CI project. We're using GitLab as our basis for hosting a trusted copy of our source code. So all of the development teams continue to use their own, GitHub or GitLab open source repos, repositories. But then we have a trusted GitLab instance that's supported for us in another U.S. government agency, OSCE. And from that, we have runners that has a growing number of platforms where the runners can then obtain any updates from the trusted repo and then execute tests on behalf of the development team. Doing regression testing, sanity tests and things like that, so that we can reduce the amount of time between the introduction of a regression and the detection of it, especially on these leadership platforms, which often have very different software environments than what the development teams have direct access to. So this remote CI capability is very powerful for us. Okay, I wanted to talk a bit about the SDK, the software development kit. Software development kits, as I said, have these common attributes. There's a common domain scope, there's an interaction model, selection of community policies, there's this meta infrastructure, reporting, planning, and community outreach. Of the SDKs that we've been working on, by far the most mature is the Map Libraries SDK, or sometimes called the XSDK. The XSDK has developed its own set of community policies. I have them listed here. I won't go through these in detail, but essentially there are statements of best practices, common look and feel, that allow the users of these independently developed products to have a more high-quality experience using one or more of the products in the SDK. They also actually turn out to be, in a sense, the entrance criteria or the acceptance criteria for another library or another product that wants to come into the SDK. If somebody wants to join the Map Libraries SDK, they have to be able to address each of these mandatory policies and, to the extent possible, the recommended policies. And this has been our way of growing what the XSDK, the Map Libraries SDK is, in a nice, uniform, and rigorous fashion. We've done now 5 releases of the Map Libraries SDK. This was back in December of 2018, everything that was included in it. You may notice that there's a package, for example, FIST, which is to the right of the green bubbles. That's actually a solver library developed at DLR, the German Aerospace Research Center. But they wanted to be a part of it, so even though there's no DOE funding, not even any US funding for it, it easily fits into the XSDK. They use components of Trilinos, so now that we've maintained compatibility between what they provide and the version of Trilinos that they use. And so this is a way for us to grow the set of compatible libraries. This is the latest version. This is a stack diagram. I won't go into detail, but it shows you some of the relationships between the various packages. Here, this is the current list of 21 math libraries and 2 domain-specific packages, and you can see the growth in the various versions. And just because all of these are available doesn't mean that you have to build them all. We build and test them all so that any subset that's needed, for example, if you need to use sundials, and sundials depends on a subset of packages, you just build sundials and everything that it needs, and that's all you build. And so it's a nice way of providing a consistent full experience for the users of even partial subsets of what the users need. And then, even though we don't build all against all compilers and all configurations, similar builds should work for similar or less, hopefully less work than just doing it all on your own. The key thing in terms of functionality that we provide in these SDKs is version compatibility. So, for example, Pepsi does a very good job of managing the versions of software it uses. Trilinos does as well. We each know what we need. But prior to the XSDK, there was no management of the version of SuperL each of us would use. And so these SDKs allow us to manage horizontal grouping by negotiation and by building together a common set of libraries. I won't go into this in detail. These are the newest release of policies. Again, these are in your slides. And then this is how teams join us. And again, I won't go into details because of just out of sensitivity for the time. And then we do a two-level release process. Each member package puts out a release and gives a tag. And we use Stack again in order to be part of the XSDK. You need to have a Stack package that defines how to build you and your dependencies. And that's how we build everything. So all the builds are done through a remote access to the main repository of each project. So there's not a central repository of all of this software. It's all done using Stack and distributed source access. So within the broader ECP software technology portfolio, we've replicated this approach to creating SDKs across each of the other development efforts. So there's an effort in programming models and runtimes, development tools, math libraries is the oldest one, and then data and viz. And then there's a coordinating effort within the software ecosystem and delivery area that coordinates across all of these SDKs. We've done some analysis and then grouped each of the product efforts into these colored collections of products that are in each of the SDKs. And now we're moving toward creating a set of community policies for each SDK and creating the interoperability in the SDK of the various products. Just as an example, within the data SDK, HDF5, the API of HDF5 is the most commonly used. And so there's an initiative within the data SDK to make things like data lib and audios available via the HDF API, so that a person who's already invested in the HDF5 API can access other implementations of I/O libraries without having to rewrite their interface, at least not right away. It gives them a chance to use something without a lot of effort on their part. So a little bit of a summary of the SDK effort. Again, I won't go into too much detail. You have access to it. So pulling it all together, we have individual 33 projects that contributed to 70 open source products. These are grouped into 7 SDK efforts, and then these SDKs are further build targets for the E4S product as a whole. Okay, a little bit about collaboration. We want E4S to be an open, collaborative environment. Open source is by nature collaborative and universal, international. And we want to take advantage of that by making our architecture of the software stack that ECP is building open and universal, contributable and accessible. We've worked with the National Science Foundation in the United States. We held a joint workshop with them last summer to acclimate their scientists to E4S, to both as users and contributors to it. We plan another workshop this summer. And so there's strong interest on the part of the NSF in this effort. They will also be hosting runners for our continuous integration. They want to be able to run our stack on their platforms to help decrease the effort that it would take to finally integrate our software into their environment. We want to extend this. As I mentioned, we have open source projects like DO2, which is a math library, FIST, other products that we'd like to integrate into our SDKs. We're working with commercial open source distributors and packagers, OpenHPC, the HPC system vendors, San Diego Supercomputing Center, Texas Advanced Computing Center, and others, and NSF, the National Oceanic and Atmospheric Administration, and international collaborators. And so we're poised now to begin further discussions with stakeholders in the international community, and we'd like to have that conversation with regions. I need to say that we're not starting from scratch. We didn't emerge from nothing. We're leveraging work of many others. HPC Linux, there was work done at the University of Oregon. It's no mistake that Samir Shendi is in charge of the E4S effort. He is at Oregon, and he has a Paratools company. We're able to leverage the many years of work that they've done in this area. The XSDK existed before ECP, and of course back predates E4S. I just want to mention that we do have this ARM64 base container. It's on Dr. Hub, and it actually supports NVIDIA GPUs. And so let's do a little bit of wrap. Okay, as I mentioned, we had the original set of four, or of the level, what we call level 4. These are the individual package teams. ECP allows us to then add this SDK aggregation layer of similar types with similar users and interoperability. And then E4S allows us to build an entire same stack and include other things that we don't develop. And we hope that this provides an open, hierarchical, and extensible ECP software ecosystem that we can build on as we go forward in collaboration with others. And just what is E4S not? It's not a closed system, only from DOE. It is extensively open architecture and a collaborative framework. It's not monolithic, take it or leave it. It's a manifest of a la carte collectible software capabilities, or the whole thing if you want it all. It's not a commercial product. It's for a high quality, reusable, open source product. It's not a simple packaging of existing software. It really is this hierarchical conduit for bringing things forward. So some final remarks. These software development kits provide a new software coordination mechanism. There's real value added by getting teams that are developing similar capabilities to talk with each other, to work with each other, and leverage each other's value, including people outside of the DOE, ECP, and DOE. And the E4S is a complete stack, including non-ECP products, and our architecture is open and intended for collaboration. And then the final thing I'll mention is our capability assessment report. We just put it out this month. It has a very extensive description. It's hierarchically organized with a description of ECP, a big picture for software technology, each of the technical areas, and then there's a couple pages for each of the product development efforts going on. You can get a lot more detail in that document. And I'll stop here. Thank you.